I start deforming it, so I start pulling the upper part and lower part, then what happens after some point, it will look like this. It will blunt. Okay? And if you remember our last discussion, the plastic zone correction by Irwin said that you can imagine that this blunting has resulted in a virtual crack extension. So, because of blunting, you will still have a drop in the load displacement curve. Okay? Usually this drop happens because of crack growth, but it will also happen because of blunting, because it resembles mechanically a scenario where it is equivalent to a crack growth. Okay? Material has deformed in such a way that it looks like, it feels like, according to the force displacement curve, that there has been some amount of crack growth. If you have a very ductile material, then you will see that you will have this part very large, where you will not see any crack growth in the specimen, but still the load will go down. Okay? So, to exclude this part, so this part, as it looks like there is a crack growth in the data, you don't want to take that as a crack growth, right? So, what you want to know is, you want to be sure where this blunting ends. In order to make that sure, what standard defines is that you draw a line which is called blunting line, and that line can be given as J is equal to 2 into sigma flow into delta A. Okay? So, you draw this line, so that means you are drawing a line between J and delta A, which has a slope of 2 into sigma flow, and sigma flow in this case is the flow stress, which is defined as average of the yield strength and ultimate tensile strength. Okay, so we are taking an average value because blunting, the stress is somewhere between sigma naught and sigma UTS. So, we do not know where the stress value is, somewhere between these two. So, we take an average value, and another assumption here is that this half, what is this distance? This is half of crack tip opening. Sorry, I have to draw a middle line, and then that distance will be, so the total distance will be, is called and denoted as delta, is called crack tip opening displacement, this distance. Okay? Half of that, it is assumed in this case, is equal to the crack extension. So, if my crack has blunted like this, then I say that this delta A is equal to this. This is an assumption. So, I am saying that a crack extension of same amount as half of CTOD would have happened virtually, and that gives me a blunting line. So, I want to exclude that blunting effect, and therefore, I draw this line which may intersect the initial J delta A curve somewhere here, right, and this point, this value of J is J1C. If you cross this value, let us say this value is 20 kilojoules per millimeter square. So, the unit of J usually is Newton per meter or millimeter. So, if I have to change it in joules, it will be Newton millimeter divided by millimeter square. So, that will be kilojoule per millimeter square. Yeah, so that is right. So, if you say for some material J1C is 20 kilojoule per meter square, then it means that once you applied a force which results in an energy of more than 20 kilojoule per meter square, then a crack growth will start in the material. Okay. So, this is what it means, and you can also do some other kind of calculation. So, if you want to know that if crack has extended by 2 millimeters, let us say, so how much energy has been taken by the material in order to have a delta A of 2 mm, and for that calculation you will need more than this. You will need this equation also. So, this equation can have a parabolic equation, right. So, J is equal to some constant into delta A. It can be a power of it also, which may look like this, right. So, you will need this information. So, you will need not only this point but that point also in order to find out how much energy is consumed for a crack extension of some significant amount, 2 mm, 4 mm, whatever. Okay. So, this is how the testing for J integral based fracture toughness is done, and we obtain this parameter, and we can do it on CT specimen, we can do it on SENB specimen, we can also do it on some other specimen, whatever kind of specimens are standard. So, as I have mentioned, the standard for this type of testing is defined in this ASTM E1820. But this is not all about J integration. Although we have said that J integration is not valid when there is a crack extension, we will see that there is a better way of finding this behavior by using one specimen and not 6 or 10 or many specimens. Okay. So, to avoid the effort of people machining, manufacturing those specimens, pre-cracking those, and that will include a lot of human error because you are involved in many specimens, it is better to find out the material property from one specimen if it is possible, and people found a way to do it, and that is what we are going to discuss now. But before that, there are some intricate details about experimentation which we will also it is important for us to understand. So, that is this, that initially I have loaded a specimen, right. How do I make the pre-crack? That part we have discussed, that I do a fatigue loading and I make a sharp crack, and that sharp crack has come from fatigue or cyclic loading. So, that is called fatigue pre-cracking, right. Then I loaded this specimen. After I loaded this, there will be some crack growth, right, or some amount of blunting or some crack growth. If not, you want to know at least what is the initial crack length, but initial crack length you cannot get only by looking at the surface. Okay. So, if you have fatigue pre-cracked the specimen till this point, how do you know what is the length? You will be looking at the surface only, right, but what about inside? So, we are not sure what has happened inside, right. In order to do that, you perform a test, so it will blunt, and maybe you are following this method. So, you do not want to do a crack growth analysis. So, you are testing on a stationary crack, and as soon as crack starts growing, you stop the test, okay, and you exclude the data which has happened once the crack extension has started. Okay, that is how you do this. So, then how do you know what is the crack length? Because this may not be the real crack length. So, this dimension may not be the real crack length, because inside the material, so this is only at the surface. So, how do you do it? How do you do it? After doing the test, you again put the specimen in fatigue and let the crack completely grow, so that the whole material is broken. Why do we do fatigue pre-cracking? Why not just pull it in the specimen and break the whole thing? because if you break it, you will never know where did you start and where did you end. Okay. So, now let us assume that this specimen has broken and we have not done fatigue pre-cracking. So, how will it look like? Okay. So, if I look at from the top, once I have broken this specimen, okay, I have broken this specimen, and so this is CD, and the other side, let us say, so let me draw the inner part also. So, let us say the other point here, and then you will have another point there also. So, that is CD and A and B, let us say it is that. Okay. So, now I am looking at A, B, C, D from the top, okay, and I am looking at in this way. So, this is my A point, this is my B point, this is C, this is D, right, and it has broken. The fatigue pre-cracking at the surface was here, but inside it has a shape like this. Okay. So, it is not like this, but it is like that. So, if this dimension was, let us say, 10 mm, then can you take 10 mm as crack length? No, because here it might be 12 mm or 11 mm. Okay. So, then what should be the crack length? Should it be 12 mm? Should it be 10 mm? What should be the crack length? So, ASTM standard says that you have to divide it in 9 sections and take the average of those 9 values. So, you obviously will be measuring at certain points, right, and each one of us may take 100 points. Somebody wants to be very, very accurate, and so he will take 200 points and he will say so what is the length here and what is the length here, and then he will take an average of all those 200 values and he will be getting a different value in 4th decimal place, right. So, in order to standardize that process, ASTM says that you have to take 9 values equidistant from each other, and then there are some protocols to avoid problems like, so what ASTM standard says is, like, if this is the crack tip, so what you do is, first of all, the standard says that you exclude some portion from the surface, okay, because at the surface you usually have plane stress conditions. So, you do not want to take that part in the calculation, right. Then the remaining part you divide it in 10, sorry, you have to take 9 points. So, 1 point becomes this, 1 point becomes that, right, and now you have to take 7 more points here. So, 1, 2, 3, 4, 5, 6, and now I have to make one somewhere. So, we will make here and forget about that one. Yeah. So, this is my, sorry, this is my 1, this is 2, 3, 4, 5, 6, 7, 8, 9. So, at these 9 points I take the length, this whole length, okay. So, this distance, then that distance, and so on, and then depending upon where they are, you have a special average formula which is used to take the average value of these 9 points. We do not give equal importance to these points on the sides as we give the importance to the center point, because, and why are we getting this shape? Why the crack tip is not simply this inside the material? The reason is sigma ZZ or sigma ZZ, which has a distribution like this along the thickness, right. So, the constraint increases in the constraint is maximum in the center of the specimen and minimum at the surface of the specimen, and it has a gradual increase from the surface to the center, and because of which the crack has this shape, right. If you have more constraint, the crack will open up there very easily. If you have less constraint, that means material can flow a lot because it is relatively free. So, the crack will not grow that much there, right. And that is why if you look at it from this side, okay, if you look this specimen, if you do this kind of testing and look at from this side, then or from top also. So, initially if the specimen was like this, after deformation it will actually, the crack will grow like this, and then it will actually be like this. So, and initially it was like this, okay. So, what has happened is the material has sunk in from the sides. Why that has happened? Because surface is relatively free in comparison to the center. Center is not getting material easily from all the sides, but surface is getting the material from this side, from that side. It's like jumping on the bed. When you jump on the bed, the surface sinks, right. Similar to that, you are pulling this part in the top direction, and the material is flowing in from the sides, and that is why you have this kind of shape, okay. And that is why the crack tip has this kind of structure. So, we will stop here in this lecture, and in this lecture we try to understand how we calculate fracture toughness for a plastic material, predominantly plastic material, unlike what we learned for Griffith's criteria, which was completely brittle, and also Irwin's stress intensity factor, which worked for moderately plastic material as long as the plastic zone is 50 times smaller than the smallest dimension of the specimen. We were good to apply the concept of K1C. In this lecture we learnt about J integral concept, which comes from the conservative field. How do we get it experimentally? How do we calculate the experimental value of J integral? How do we find out the J1C value from J versus delta A curve? And we learnt it by doing or testing several different specimens at different crack lengths. In the next lecture probably we will have a look how can we, or if can we do it with using one specimen, okay. Thank you.